All right, so now this area so far function is going to earn its keep. So what I have now is that we're going to consider this function. Remember, the lower limit is allowed to be anything. I'm going to choose this lower limit to be 1. The function we're going to be working with is 1 over t, the ordinary reciprocal function that you probably played with in a basic algebra course. Now, I'm going to make the requirement that t is greater than 0. If you do not make this requirement, remember the graph of the reciprocal function looks like this. It has a vertical asymptote of 0, and that means we don't have a derivative there. So, by making this requirement, that guarantees that we're only using this piece of the picture, which means it is continuous and it is differentiable. And so we have no holes, no jumps, no vertical asymptotes, and no cusps to worry about. This is an area so far function. This, I'm going to name this function. Now, again, what this means is, if I want to evaluate this function at a particular value of x, what it means is you substitute into this numerator, and then you compute the area so far function. But what's happening here is we're starting at x equal 1. Unlike the previous example, by the way, the previous example we worked through, you do not need to be able to reproduce that at all. That's just some backgrounds, baseline information to get to the notion of understanding this. So what we're doing is we're starting at 1, and as x gets larger and larger, we get more and more and more of this area. We may also choose x to be between 0 and 1. We could choose x to be 1/2. Now see what that means. If we choose x to equal 1/2, that corresponds to the integral from 1 to 1/2 of 1 over t dt. That means we're going to take 1, and here's 1/2. We're going to find that area. However, notice that we're starting, lower limit of integration is 1. We're starting at the right endpoint and finishing at the left endpoint. We are going to accrue this area from right to left. And recall that as you accrue area from right to left, the integral will interpret that as a negative value. So any value between 0 and 1, this integral will use that value, the input of 1/2, this will produce a negative value. Any number that's greater than 1, if the value we choose is greater than 1, let's suppose we choose 5, then we start at 1. So that would be the integral from 1 to 5 of 1 over t dt. That would correspond to starting at 1 and accruing more and more and more area. Now, we of course know what happens if we choose x to be 1. If we choose x to be 1, then the upper and lower limits of integration are equal, and that value is equal to 0. This function that we're talking about here, this function is one that you've probably dealt with before. It has a special name. That is the natural log function. You probably wonder why in the semester so far we haven't talked about natural log yet. The reason is because in order to get the natural log function, the way that we're going to define this, we needed to have the fundamental theorem of calculus. This is the natural log function. And you are probably familiar, I hope you are, familiar with the natural log function. This is the graph of the natural log function. And if you have a calculator, you can compute the natural log of any number you like. The domain, the value must be, the domain of the natural log function is x must be greater than 0. Well, why is anything that's true about the natural log function is true because of this circumstance. Why is the domain of the natural log function only x values greater than 0? Well, because if I choose x to be less than 0, then I've chosen an x over here that's outside the domain of this function, and you've crossed over this vertical asymptote, and this antiderivative no longer exists. And so for that, and a few other technical reasons, we don't allow the x value to be chosen to be less than 0. So that's why the domain of the natural log function, is, we'll write it this way, 0 less than x less than infinity. the value of x must be a positive number. What else is true of the natural log function? Well, we know if you compute on your calculator the natural log of 1, you get 0. Why is that true? The reason the natural log of 1 is equal to 0 is because that's what the calculus requires. One of the reasons the natural log and exponential is so challenging for basic algebra students is really the natural log function and the exponential function, they are calculus ideas, and we try to, we sort of gloss over that part of it, and we deal with them in the pre-calculus setting, but really this is where the behavior comes from. The natural log of 1 is 0 because if you put 1 here, the upper and lower limits of integration are equal to each other, and that integral is equal to 0. All right? As x gets larger and larger, as we move further and further and further out this axis, the value gets larger and larger and larger. That's why this curve increases. But notice, because this is the reciprocal function, if you go out to 10, yeah, you've increased over 9, but not by very much. Because this curve is getting closer and closer, it's asymptotic to the x-axis. So if we go, here's 9 and here's 10, yes, it is a slight increase, but not by very much, because you're not getting more. In fact, the further out you go, the less area you begin to accrue. And so that's why the further out you go, this curve gets more and more and more shallow. However, it never levels off because no matter how far out you go, you do accrue a slight bit more area. And so the very graph of the natural log function comes from this very definition. All right, so what that means is every time you mash your natural log button on your calculator, this is really what's happening. It's not the same computation, it's done differently. But this is the idea of what's happening here. So this is now a new function. We have a new function, f of x is equal to natural log of x. And natural log of x is defined to be the integral from 1 to x of 1 over t dt. So that's our new piece. This is the new function. This is a natural log function. This function passes the vertical line test because it's a function. It passes the horizontal line test, so it has an inverse function. So it has all these wonderful basic properties. All right? So the next piece we're going to do is talk about how do you do the calculus with the natural log function.